Basic concept of thermodynamics. Thermodynamics. The word thermodynamics was derived from the Greek words therm means heat and dynamics means force. So, thermodynamics is essentially the study of forces due to heat or heat due to forces. Now, we can say that the study of the flow of the heat or any other form of energy into or out of a system as it undergoes a physical or chemical transformation is called thermodynamics. Thermodynamic terms. System. A thermodynamic system or simply system is that part of the universe which is under thermodynamic study. Surroundings. The space outside the thermodynamic system is known as surroundings. System boundary. Anything which is separating the system from the surroundings is called boundary. The boundary may be real or imaginary, rigid or non-rigid. It may also be permeable or non-permeable, or adiabatic or non-adiabatic. Universe. The system and the surroundings combine to make up the universe. Types of system. Types of system. Depending on the nature of the boundary, thermodynamic system can be described in three different ways. They are open, closed, and isolated. Now, what is open system? An open system can exchange mass and energy, usually in the form of heat, with its surroundings. Closed system. A closed system is one in which energy, but not mass, can be passed to or from the surroundings. Isolated system. An isolated system is one that can transfer neither mass nor energy to and from its surroundings. Here are some examples of these three systems. On the basis of composition, there are two types of systems: homogeneous system and heterogeneous system. Homogeneous system. When a system is uniform throughout, it is called a homogeneous system. This system is made of one phase only. Examples: a pure single solid, liquid, or a gas, a mixture of gases or liquids. Such a system has one phase only. Heterogeneous system. A heterogeneous system is one which consists of two or more phases. It is not uniform throughout. Examples: water with ice floating on it, ice in contact with water vapor. These two systems have three homogeneous bodies, such as water, water vapor, and ice. The chemical compositions of the three phases are same, but they constitute separate phases. One more example is two or more immiscible liquids. Thermodynamic properties. Thermodynamic properties are defined as characteristic feature of a system, capable of specifying the system state. These are all microscopic in nature. In general, thermodynamic properties can be divided into two classes, and they are intensive properties and extensive properties. Now, what are actually called intensive properties? An intensive property is a property of matter that depends only on the type of matter in the system and not on the size or the amount. For example, chemical potential, concentration, pressure, temperature, density, refractive index, specific heat capacity, melting and boiling point, color and viscosity. Explanation. If a glass of pure 100 ml water and a beaker of pure 1 liter water is uniform in temperature, which is 20 degrees Celsius, then concentration, density, melting and boiling point, refractive index, color, viscosity, specific heat capacity has to be same. An extensive property is a property that depends on the amount of matter in the system, such as amount of substances, energy, enthalpy, entropy, Gibbs energy, heat capacity, Helmholtz energy, internal energy, mass and volume. As we know, extensive properties are proportional to the amount of substances. So, if we increase the number of solid cubes, then amount of substances, mass, volume, heat capacity, internal energy, enthalpy and energy has to be increased or decreased. State of a system. A thermodynamic state of a system is its condition at a specific time that is fully identified by the values of a suitable set of parameters known as state variables, state parameters or thermodynamic variables. So, how you define the state variables? When the properties of a system define the state of that system is called state variables. Explanation. Consider a gas in a beaker with a movable piston. This is represented by state 1 and it is having a fixed value of pressure P1, volume V1, temperature T1, etc. Gas can be cooled or heated either in constant pressure or constant temperature or constant volume, etc. Then the gas is changed in another condition. The new condition is represented by state 2. At state 2, it is having another fixed volume of pressure P2, volume V2, temperature T2, etc. Therefore, the state may be represented, identified or described by certain observable microscopic properties such as volume, temperature, pressure, concentration, internal energy, enthalpy, etc. State function. A state function is a thermodynamic property of a system whose value depends only on the present state of the system and is independent of the path by which the state was reached. State function is also known as point function. Explanations. Consider a mountain climber hiking up a mountain. The climber may decide to take path A, which is steep route, or path B, which gradually winds up to the top. But climbing up by the direct route, which is path A, is more difficult as it is almost vertical than the curving route, which is path B. Whether the climber takes a direct route or curving route, the individual's altitude at the end is the same. Thus, altitude is the state function because it depends only on the final destination, not how the climber got to that altitude. Similarly, volume, pressure, internal energy, enthalpy, entropy are the state functions. Path function. A path function is a thermodynamic property of the system whose value depends upon the path by which the system changes from its initial to final states. Let's see an explanation. Let us consider two cities, A and B, are connected by a straight line and its length is 100 km. There are two more routes linking A to B with lengths 150 km and 200 km. If the distance traveled by a car from A to B via route 2 or 3, then work done and fuel consumption are dependent on the route and the mileage of the car. However, the locations of A and B are fixed and they are independent of the routes. Hence, the two cities A and B are the state functions, while fuel consumed and work done are path functions. Similarly, arc length and heat. Both are path functions because their magnitudes depends on the path followed during a process as well as the final stage. If you like this video, please like and share, and if you have any suggestions, you can write down on the comment box, and please don't forget to subscribe to our channel. Thank you for being with us.